All right, hello everyone. Hope everyone's doing well. I'm Vincent Matossian. I'm a software engineer in the infrastructure foundation team at Facebook. For those of you who don't know, you may run into a lot of people from Facebook around. They are in the infrastructure foundation team. It is sort of the team that defines the life cycle of all our hardware and manages it. It's sort of a very cross-functional team. We do a lot of stuff in there. It goes from anything from strategy to sourcing to hardware design and engineering. So it's a very encompassing team. Within that team, I work with the manufacturing quality and the hardware validation engineers to build tools to improve the management of our hardware on the manufacturing side. So before joining Facebook, I worked in a very different field of high-performance computing, which some of you may be familiar with, hopefully. And I built workload management and job queuing systems. So it was a very different landscape. My transition to Facebook was not really the need to have high-performance manufacturing. We don't really call it high-performance manufacturing. But it was really in leveraging my expertise in automation to build and improve processes and tooling. So I always think that automation is really the key to scaling, and it's never as true as in an environment like Facebook. On a sort of personal story about OCP, back years ago when I was still in the HPC space, and I would actually research about the space to find out more about how high-performance computing centers were set up. I was looking online to figure out more about these environments, and I would always run into OCP specs. I'd be like, wow, this is amazing. They just publish all the blueprints for the data centers, and I had a lot of respect for the community. So it's a big thanks to all of you that are making this happen, and it's really encouraging because the impact goes way beyond sort of the hardware that gets announced and the tools that get contributed. It really impacts people that are in different fields that want to join this effort. So with this lengthy intro, here's what I'm going to be talking about today a little bit. I'm going to talk about this manufacturing testing framework that we're working on. I'm going to give you sort of a bit of context. For those of you who were here in the previous talk, you're going to see some rehashed information. I'm sorry, I didn't know the talks were going to sort of follow each other. So you're going to see some redundancy, but you're going to become experts at everything that has to do with hardware lifecycle at Facebook, I promise. So I'm going to give you this overview on the problems that we've run into as well that led to the manufacturing testing framework work we're doing. Give you an actual overview of the framework and its components, talk about what we're actively working on right now and what we have ahead in the few months working ahead in our roadmap, and talk a bit about the community engagement. All right, so this is one of them. It's only the first few slides, but you're going to get a big recap. If you weren't here, this is going to be great. This is kind of a total recap of our life cycle. So back in 2011, we introduced our first compute server. This is going to be much faster than earlier. And in 2013, we introduced our first storage chassis. And then more recently, in 2015, went into the network switch with the wedge. And then even more recently with the GPU servers. So the point to note here is that over the years, and actually one more thing about this is throughout those years, we keep refreshing these lines of servers from compute, storage, and network. And the point to note here is that we just have an ever-growing number of hardware to manage and to test. So there is more and more demand on the testing that happens for each one of these hardware. That's the sort of takeaway from this slide. With this growth came, as Brian and Craig were talking earlier, a big change and a big change in our supply chain. Back in 2011, the servers were fully assembled in Asia. So the components, the CPU, the memory, the power, the whole system. And then they were shipped in region where they were integrated into the racks. So all the servers would be inserted in the rack, and then they would go through testing, and then they would ship into the data center. So this was pretty inflexible because you have these servers that are being built in in Asia and just being tested there, then shipping, then testing again, integrated in the rack. But it worked because there was a single vendor, there were a few data centers in the US, and we could manage it. But as time went on, the model was not working as well with the demand of our data center growing so much. So we made a number of changes. We went to a configure-to-order model. And in this model, we basically get the components from Asia still, but they actually ship in region where they then get assembled into the servers and into the rack. Postponing these decisions as late as possible in the supply chain gives us this flexibility to change everything we need to change as late as possible, or as close as possible to the time we need those racks in the data center. And especially on the testing side, this really allows us to get feedback on what we really need to test based on what we see in the data center. So to anchor that point about the feedback, which is really important from the testing perspective, let's take another look as well, on not just on the supply chain, but on this evolution of the hardware. As most of you may have seen earlier, every single piece of hardware evolves through these stages, right? It goes from this hack in sort of a lab where we put these components together and evaluate them from a mechanical and performance aspect. And then it actually matures into an actual design build where it's actually ready to serve some application in some points, and then goes into mass production build and deployment throughout the fleet. And then enters this sustaining mode and eventually goes through decommissioning. Again, here the point is at every stage there are specific test requirements, right, that are directly derived by the observation we make from monitoring our hardware in the fleet. And we want to capture all this information so that we can improve our hardware from generation to generation. All right, so having said all that, now jumping into what's really the problem we're trying to solve, or what's the problem we've had. Well, one thing that we've established is that we need flexibility in our testing to adapt to this growing number of hardware types we have, right? This is just managing this hardware life cycle. And the other is now we have this opportunity with all the multiple vendors that we have that are shipping the components in region where everything is assembled and tested in region before shipping to the data center. We have this problem of standardization of our manufacturing testing process across the vendors. We need that so that we can actually compare our hardware against a level playing field, right? So that we can compare apples to apples in this case. To do that, we sort of need to move away from this unilateral implementation of our test specification. Today, we actually provide the test specification to the vendors, but we leave all the implementation details to them, which leaves a lot of unknowns for us. So we want to actually move closer and work more tightly with them and collaborate on the implementation and design of those tests. We also need more real-time visibility of the manufacturing data. So we've seen that we collect a lot of data in our data center, but we actually want to see real-time manufacturing testing data directly on the factory floor. This is really needed so we can do some analytics on our key performance indicators on all the components directly at the factory. And really all this boils down to one thing, which is sort of this overarching need for continuity and traceability of our manufacturing quality from the factory all the way to the fleet. All right, before jumping into the overview of the framework itself, I wanted to touch on what we mean by manufacturing validation. So in essence, it's all about making sure that the hardware is sort of ready to serve production traffic, right? From a manufacturing build perspective, we're going to limit the number of sort of dead on arrival components. And the goal is really, really simple. All we need is to make sure that what we've built is meeting sort of the bill of material, and we do bookkeeping on did we build the right thing? That's question number one. Question number two is when we put that system sort of under stress for a particular workload, is it actually performing within expected tolerances? As long as we can say, yeah, we replaced any component that failed any of these 2 tests, then we're good to go. We have this kind of big go green light over the rack that's just going to say ship it, and we're happy. So manufacturing validation from this perspective is really straightforward, hopefully, simple. So let's talk about the framework. We've broken up the framework into individual services and mechanisms, and I'm going to be talking about each one of them here. And just like I really like the saying about you can't improve what you can't measure, you also can't test what you can't name, in a sense. So asset management is that part. It's about naming, defining, and declaring all the pieces that have just been built that we now need to test. So this is things like for a server, the serial number, the part number, the MAC addresses of the NICs, of the out-of-band, MAC addresses of the out-of-band. It's also sort of the relationship of the server to the rack it's in, and the relationship of that server to the switch and the ports it's connected to. And in addition to that, it's also where we interface with our product lifecycle management tool, right? Where we need to query for the bill of material, get all the components and configuration that are expected in these assets. In addition to that, it's also where we need to interface with the factory's shop floor system to query for manufacturing asset information and eventually write test data so that we can keep manufacturing traceability and reporting on the factory floor. So now that we know we have named the thing, we know the racks we want to build, the servers we've built, the next part in the testing pipeline is to provision it. And provisioning is kind of a big word. It just means basically it's a process of bringing up a system, right? For example, installing an operating system or services and tools that are needed to start interacting with it. Provisioning can be really, really painful if there are discrepancies between the factory and the fleet. Because basically you've got a massive rack that's sort of a paperweight, right? It does nothing. You can't even bring any services online if there's an issue. So we try to keep the provisioning that we do at the factory as close as possible to what we do in the data center. And we try to align on things like the operating system we use, the kernel, the bootloader, and the overall provisioning logic. So one of the value of the framework is also we compile this custom RAMFS image that contains all the testing services and the testing tools that we need to query the system. And we install that on a diskless fashion, so it's just purely in memory to run the servers. And yeah, the process of creating this image is also part of the framework, which is a great value add. All right, so now we have systems that are up, a rack that's sort of blinking and happy. The next thing is, well, how do we manage execution of doing stuff on it, running stuff on it? And that's where the job engine comes in. And it's really sort of the management of all the task execution falls under a job engine. For those not familiar, basically the best way I can think of describing a job, it's basically a handle to an action that we want to perform. I can't be any more generic than that. It's a really abstract concept. Some may think, okay, this is great. I can use SSH. I can run a command over remotely. The job engine has this really nice feature to it, which is to return a job identifier, right? That's unique. And this identifier sort of gives you a handle to monitor the progress of whatever it is that you're actually doing, of your action. You can also use this identifier to either terminate the job or to rerun it. So the job engine is really tightly linked to the scheduler, because the job engine in its own is basically sort of just a launcher or an executioner. The scheduler is the part that is sort of doing the orchestration and sequencing of all the tasks and the ordering of them across the units we want to test. The best way I can think of describing a scheduler is basically determining who does what when. Right? This is kind of the brainy part of the logic, of the application logic. So it basically, the scheduler takes as input a set of tests that we want to run or a set of tasks we want to run, and it takes the units we want to run on, the servers or the racks, and and it's going to basically go and implement the execution logic. Keeping in mind that this can get complicated, for example, when you have a single server test that you want to run versus a multi-server test that you want to run. The scheduler is really responsible to figure out the placement and allocation of who does what at that point. All right, on to the tests, which are, at the end of the day, the actual meaty part of what we do. So I'll talk a bit more about the tests themselves, but in the context of the framework, the tests end up being all these tasks that are being managed by the scheduler, right? And the value here is that the framework acts as a repository of all the test cases that we want to run. So in many cases, in organization, we tend to have tests that are spread out throughout the organization, and we lose track of some of those. Having a repository that manages all the test scripts so that the versions of the test scripts are also maintained and managed has a huge impact, because without that, it ends up being quickly chaotic. All right, so now we have all these tests are running on the racks. Everything is cranking, and the next part is sort of, for all this data that is being generated, is to actually collect it. So it gets streamed out from every test unit that is cranking out the test cases, and it's actually getting logged into a log server or a file server and indexed. So we can start running some analytics and do any error detection, error trending. So this is a huge part about trying to identify failing components, right? The other is the monitoring piece, right? So if a test hangs up, having the capability to detect using some kind of heartbeat monitoring how and where the hang up is, and resolve that. All right, and then all these services and mechanisms are basically built on an API on which we build a command line interface and a graphical interface. A point on implementation, this is all written in Python, and it uses Apache Thrift for the messaging between the services. The interesting part about this framework is there were many pieces that we built in our infra at Facebook that are not ready to be open sourced yet. So we actually re-implemented a lot of pieces here to fulfill the needs of this particular manufacturing testing framework. And all of them are open source, which make this framework a lot more easy to integrate into different application domains or other environments. All right, so this was kind of like the more the dry version less visual version of the components. Let's see how basically this would flow in a typical use case. Well, the first one is you'd have a user. It could be a test operator, it could be a test engineer, a manufacturing engineer. But most importantly, it could be a program, right, that would then interact with the test server and the test services. They would, at that point, define the assets that they want to build. So in this case, let's say it's this rack that just got built, and we need to tell the services and the testing server this rack exists. So the first thing to do is to declare it and define it. At that point, it kicks off sort of a host discovery loop, and that's where kind of the provisioning of these systems happen. The user, which again can be a program, would then associate a test suite to run on these assets. And at that point, with that association is basically the job I was talking about. So run this test suite on this rack. That would trigger a scheduling loop and the execution of all the tasks on the assets. And at that point, the analytics gets collected, and we keep monitoring it, and it cranks away. So this doesn't show the remediation and repair flow, which is its own thing, but I wanted to sort of give you an idea of the visual loop of the main use case. On the testing side, what exactly do we do? Well, we do different things based on every hardware type that we build, right? But we try to extrapolate these into sort of more generic loops. And this is an example of a loop that we would run on particular types of servers. The underlying tools that we use may vary depending on the hardware types, but the first part is basically a very basic diagnostic just to ensure that the system can be reached and that it actually meets the manufacturing spec that we want to do for testing. Really? So I'll crank through that. I'm spending too much time. So this is where we would set, for example, BIOS ECC thresholds. Then we would run a network performance test to make sure that the throughput between the servers in the rack are actually meet our expectation. We'd stress the memory interface to make sure that this is not catching any issues with the DIMMs. We'll AC or DC cycle. We will stress the CPU. We will stress the storage. Do another round of warm or cold reboot to try to catch any issues. And while all this is going on, we will frequently run configuration checks to catch any issues with the components for fan speed, battery, PCI. And this will continually run, and if any of these fail for certain criteria, it will actually fail the whole test. All right, quickly through the how these test cases get woven through into a test suite is, so one of the value add of the framework is this YAML specification, where we can take in a non-programmable way, associate these test cases and have a non-programmer, it could be a manufacturing engineer, write the test case and pass specific attributes or properties of that test into the test suite. So these could be the arguments of the test case, for example, the number of retries that each test case should make. It could be the number of nodes that it wants to run and so forth. And so the typical practice is you'd identify all the tests you want to run from the stress and config checks you want to do on every component, compute, memory, storage, network, and then see if there are these test cases in the framework and then put them together. And on the top right is kind of a very basic view of a YAML file that would be created. A lot more to be said about that. Find me later if you want to talk about it. A view of the GUI that we currently have is scrubbed, so it's very blank in some areas. But the idea is here to have access to information for the racks, the switches, the servers, as well as the jobs and the tasks that are running and currently in the system, and then a view of the test suite and the test cases. It's also where we can submit a job into the system and where we have access to all the asset operations for scanning in a rack, scanning out a rack, swapping a server within a rack. And what we see here is basically every job that was submitted, say, at a given stage. This is a testing stage, not the hack through DCOM stage. This is just a testing stage. And it basically gives us a quick view so a test operator can dive into the logs and do some debugging and analysis. This is a similar view, but it's more visual, again scrubbed, so apologies for the awkward look, but it's basically another view for an operator to locate a server that may have failed and just dive into the logs and see it visually on the actual rack. And this is a view of a dashboard that was put really quickly to investigate something in terms of the number of pass-fail over a certain given period of time. This, some of you may recognize, it's the Kibana front end to an Elasticsearch store that we use to centralize the logs. So the next steps are, we're currently working on applying this to an ongoing reliability test pilot for measuring the MTBF of our servers. And we're working on the core development of the framework. So on the reliability piece, we're focusing on the sort of redundancy of the services we need to build to do the capacity planning to figure out how many services we need to build a given number of racks concurrently. We're also building a collection of analytics dashboard for our KPIs, improving the graphical interface, which needs quite a bit of polishing, working on storage management so we can offload some of the data from the factory floor and retrieve that into our data warehouse, and further our integration with the management execution service at the factories. So we are considering open sourcing the framework, but we have very little clue on what the field is like, what the engagement would be like, because we don't want to just put it out there and just let it drop and just be the only ones to maintain. So we're interested in hearing from the community about this. Manufacturing testing, everybody's got to do it at some point. We don't know if such a general purpose framework would actually have a good audience. So feel free to find us and tell us about your pain points, anything that you've actually had a hard time implementing or the types of hardware that you're building. And that wraps it up. I'm sorry if I was late. Thank you very much.
Anybody have any questions?
A real quick one. Did you, for like the CPU and the memory stress testing, did you build your own tools for that, or did you use stuff that was already available?
We're using a sort of a bunch of open source tools for that. And we're always on the lookout for diags built in-house. So that's one of the value of this framework, is that we want to take some of the work that's done in the hardware validation team that is run in-house and actually bring that over to the factory, which is not something we're doing right now. Not yet, but yeah, not yet. Yep. You mean for out-of-band access to sensors?
Like your manufacturing hardware, factory floors, all of that process.
Yeah, I mean, we are putting together sort of a whole, I don't know if that will answer your question, maybe we can talk offline, but we are putting together a whole spec for the hardware we want to deploy there, as well as the software we want to deploy. But maybe we can talk offline, so I get a better sense. Sorry. Yep.
You feed the failures from production into the same data warehouse you use when you do your manufacturing testing?
That's a great question. Not yet, but that is something, that is definitely the plan. Yeah, absolutely. Yeah.
So
It gives us convergence. Absolutely, absolutely. Yep.
Okay, I think we have to stop now.
Yep, thank you very much.